to give you some notes here for Taylor series error bounds. The first thing we're going to talk about is when you have an alternating series, and this is really exactly the same thing as what we already know about alternating series, that the error is not more than the next term or the first term that you didn't use in your approximation. That's just a tiny bit different feel because we're working with a series that has the variable x in it, but let me just give you an example, show you what I mean. So for example, the series for the sine function is x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, etc. So what if we were going to just use the first term as an approximation? So consider what we could say the first degree approximation. We could say this is a tangent line approximation, that sine x is approximately equal to x, just the first term. The tangent line to the sine function at x equals 0 is the line y equals x. Right? We've known how to do that for a long time. We also have that here from the series. So how good is this approximation? We could ask the question, for example, for what interval of x values is the sine x approximately equal to x good to 2 decimal places? That would be a pretty decent approximation, right? If it was good to 2 decimal places. So let's see how we can figure that out. Well, we know since x minus x cubed over 3 factorial, etc., is alternating, and the terms are approaching 0, that means that the actual value of sine x minus the first degree approximation, which is just x, is less than the next term, x cubed over 3 factorial. So if we want to know for what values of x is this approximation good to 2 decimal places, we just need to figure out, we basically need to look at this inequality here, x cubed over 3 factorial. We need that to be less than or equal to, because if I put something over here that it's less than or equal to, this is still a strictly less than sign. So that'll still give us less than. Remember, 2 decimal places is 0.005. So let's see, doing a little algebra here, x cubed would have to be less than or equal to 3 factorial, which is 6, times this, that's 0.03. Our x would have to be less than or equal to the cube root of, excuse me, the cube root of 0.03. And to do a cube root on your calculator, you can raise something to the 1/3 power. And since I want it to be good to this approximation, I need to round in to make the interval tighter rather than looser. So instead of rounding to 0.311, I'm going to round to 0.310. I'm going to round conservatively to make the interval smaller. Right? And also point out that I should have put here that this is the absolute value of that next term. So that means x needs to be between here and here. So those are the values of x that will, if you're going to take the sine of x and compare that to x, then we're going to be good to 2 decimal places. And I'm just going to show you on the calculator. I'm going to go to my y equals and put in here 2 functions, the sine of x and then just the function x. And then I'm going to go set my table up so that I'll just look at the positive values, that it goes from 0, and I'm going to go up by hundredths, 0.01, and I want that to set up automatically, and I'll go to the table. So if you look at these values, you can see these are the values of the sine function, and these are the values of just y equals x. And we can compare them and see if they're good to 2 decimal places. So all the ones on this screen are, and I'll keep scrolling here, I'll get to about here, we'll see, is it still good? 0.26, now round to 0.26, still good. And then when we get to about 0.31, that one, you can see 0.31 rounds, 0.305, it just barely rounds so that they would be the same. And as soon as you get to 0.32, that's the first one that does not round to the same thing. So if you want accuracy to 2 decimal places, you need to be inside this interval. These are the x values where our approximation, just first degree approximation x, is good to 2 decimal places. Excuse me. So, this is an important thing for physics, it turns out, so just a quick comment about this. These are, of course, when we do calculus with trig functions, we're always in radian mode. It might be curious to just know what we're talking about in degrees here, so we could just do a quick conversion. Multiply by 180, divide by pi, to see if I take 0.310, multiply by 180, and divide by pi, that we're talking about 17.7 degrees or so, so about 17 degrees-ish. And in physics, if you're in AP Physics, we're going to call this the small angle approximation. If you're using the sine function, the sine of an angle, you can actually replace sine x with x and be confident that that's a good approximation as long as the angles you're talking about are fairly small. And fairly small, we'll typically say in physics that it's between about positive and negative 15 degrees. It's really a little bit bigger than that for 2 decimal places. So there's an example of an error bound there. I'll give you one more example of it with an alternating series. The tangent inverse function has a series. This is one of the little 2, so maybe just pause for a second and see if you can remember what that series looks like without looking at your notes. Are you back? Did you really look? Give you another chance to pause. Actually looks a lot like the sine series, except without the factorials. Oops, without the factorials, as I was saying. So, looks like that. So, we might ask, what is the error if we approximate tangent of, let's say, the tangent of pi over 4 is pi over 4, pi is about 3, so we could say, let's just say, so we can do it with our calculator, the tangent of, say, 3/4. That's an angle that's pretty close to pi over 4, and we know that the tangent of pi over 4 is 1. So we could approximate that error. What's the error if we approximate that with the 5th degree? In other words, the first 3 terms. 5th degree Taylor polynomial. Well, I'm gonna set it up like this again because it's a good idea to get familiar with writing things like this and understanding what this means. And you could pause for a second and think about what that should look like. So the tangent of 3/4, that's that thing we're actually looking for, minus the approximation that we get when we plug 3/4 into this. So if I didn't feel like simplifying it right now, I could actually just put it in here. So that's 3/4 minus 3/4 cubed over 3 plus 3/4 to the 5th over 5. That's the approximation. That is going to be less than the next term, which is 3/4 to the 7th over 7. So that's how good our approximation is. And I'm not going to do that by hand. I'll go ahead and use a calculator. This would be likely some kind of calculator problem here. So 3/4 to the 7th divided by, divided by 7. We're on to 3 decimal places. And then I'm also going to, I didn't put absolute value signs around that because clearly that's positive. I'm going to also run this through the calculator. This is my approximation. So let's see, that's 3/4 minus 3/4 cubed over 3 plus 3/4 to the 5th over 5. So that's about 0.657. So the difference between the actual value of tangent of 3/4 and the approximation that we got using the first 3 terms is this. So what's the range of possible values? I think this is an important thing to think about to understand what this says. Well, this basically says, like, we're not off by more than this in either direction because of the absolute value signs. So one way of writing that, if you want to go through the algebra, if that makes you feel good about things, then that's the same. This absolute value inequality is the same as saying that difference between those two things right there is in between negative 0.019 and 0.019, right? That's the error, so it's plus or minus that much. And then I could add this to both sides of this inequality and get, what would that be, 0.638. And then add that over to this side, that would be 0.676. So whatever the tangent of 3/4 is, we can be confident because of the alternating series error bound that it's between those. And now we'll just check that and see how we did. So tangent, and it will probably be pretty close to one end of that. Usually we're off by close to that much. So we'll see which end. 3/4. Oh dear. Oh, sorry. This is the tangent inverse function. So I'm doing tangent inverse of 3/4. So doing tangent inverse of 3/4 of pi over 4 is kind of a silly thing to do if you think it's going to be a nice number. I apologize for that. Let me just do that again. So tangent inverse of 3/4, and we'll see that it's 0.643, so it's a little bit closer to this end of the interval. So sure enough, we were off by less than this, and that was our guarantee. We were not going to be off by more than that. So you can do alternating series error just like we did when we were doing series. It's just that you're plugging in an x value now, and it makes this look maybe a little bit different. Now, what if the series is not alternating? If the series is not alternating, then there is something that we can use that's called the Lagrange error bound. That's for non-alternating series. If you have an alternating series, you don't want to mess with this. You don't need to. The Lagrange error bound. The Lagrange error bound says that if, this is a big if you know that the n+1 derivative of your function is less than or equal to some number, I'm going to call this m, like for maximum, right? So if you know that your next derivative is capped by some number, it can't be bigger than this, on a closed interval that contains the x value that you want to approximate. So that just means that this would have to be true. If you're trying to approximate at x equals 2, then you'd have to know that this was true on some closed interval that included 2. That's all that means. Then, the difference between the function and the nth degree approximation, whatever that happens to be. So that, for example, in the tangent inverse problem we just did, the nth degree approximation was this, right? So the difference between those is less than m times x minus c to the n+1 over n+1 factorial. That's kind of like the next term, right? If you think about the way that you make a series, if you put this in place here, that's basically like the next term of the series. And the c is whatever the center of the series is, right? So if your series is centered at 1, that would be an x minus 1. If it happened to be a Maclaurin series, this would just be x. Right. Let me give you a couple examples of how this could work. So, example. use the first, let's say, 5 terms of the Maclaurin, means centered at 0, Maclaurin series for e to the x to approximate e. And notice that, of course, e is e to the first power, right? So the first 5 terms. So e is approximately equal to 1 plus, then I'm plugging in 1 for x into the series. So maybe I'll just make a quick note here. Remember that e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial, etc. And that's the first 5 terms there. So it would be 1 plus 1, right, because this is e to the first, plus 1/2 plus 1/6 plus 1 over 24. And so there's an approximation for e. How good is that approximation? Well, I know that the actual value of the function, which is e, minus this approximation, which is, we can just figure it out. I feel like we could almost get that. Let's see, common denominator, let's see, do it without our calculator. 24, so I would have, this is 1/24 plus 4/24 plus 12. So 1 plus 4 is 5, plus 12 is 17. So 2 and 17/24. So the difference between e and this approximation of it using those first 4 terms is not bigger than, here, I'll do this part first. So the x is 1 minus the c in this case, this is a, you look at all the x's here, they're all minus 0. So that to the 5th power, right, I use the 4th degree approximation, so that's 5th power over 5 factorial. And then the question is, what do I put here? Do I know some kind of maximum value for the 5th derivative of e to the x on an interval that contains x equals 1? Well, the thing about e to the x is all the derivatives of e to the x are just e to the x. So the 5th derivative of my function is just e to the x. And on an interval containing 1, if I thought about the interval from, like, say, 0 to 1, this is increasing, and I know that e to the 1 is just e. And now, I don't want to use the value e to approximate e. That would be kind of bogus to do. But I could, like, just round up a little bit and say, you know what, e is, like, it's close to 3. So without losing too much of my accuracy here, I could say that, right? That's definitely a maximum value. I know that the 5th derivative of e to the x on an interval that contains 1 is definitely capped by 3, right? It's not going to be bigger than that. And then let's check this out and see how we did. So that means, let's see, that's 3 over 120, right? That's 1/40th. So it means that e, the difference between e and my approximation here, is not more than 1/40th, plus or minus. Oops. And just to check, 1 over 40 is that 0.025? Yeah. So I'm not off by more than that. So let's go ahead and check that. So e, well, e is that, right? And then 2 and 17/24 is that, right? So the difference between those is, it looks like it's about 0.01. And this was 0.025. So that was good error bound, right? We were not off by more than that. You notice that the error bounds can be a little bit conservative, right? I mean, we were actually considerably closer than that, but that's the error bound we got from using that right there. So there's one example of the Lagrange error bound. Sometimes you're given problems where they just tell you a cap on that. They basically just give you the m. So here's one last example. So consider function f of x with f of 3 is equal to f prime of 3 is equal to -2, and f double prime of 3 is equal to 4. And let's say we also know, we just happen to know, because somebody told us, a little birdie, that f prime of x is less than or equal, f triple prime of x, so the next derivative, is less than or equal to 3 for all values of x. So we don't have to worry about our interval. It's just true for all x. That means we can use this as our maximum value. So we're going to try to use the second degree, because I have function, first derivative, second derivative. So use second degree Taylor polynomial for f of x at x equals, I have to make it at x equals 3 because those are the things that I know about, to approximate f of 5. So let's go ahead and do that first. So first thing I have to do is make that second degree Taylor polynomial. I'll call that T2 of x. So let's see, the recipe for a Taylor polynomial centered at x equals 3, it's f of 3 plus f prime of 3 times x minus 3 plus f double prime times x minus 3 squared over 2 factorial. There's my second degree polynomial. If I want to approximate our 5, that's 2 minus 2 times 5 minus 3 is 2, plus 4 times 5 minus 3 is still 2 over 2 factorial. So that's 2 minus 4 plus, that's 16 over 2. So that's -2 plus 8. That's 6, I think. You can check that. 2 minus 4 is -2 plus 8. I think that's right. And then use the Lagrange error bound to find the error. Actually, let's say it this way. What's the difference? So you got to get used to seeing these. What's the difference between f of 5 and T2 of 5? So let's use the Lagrange error bound to find what needs to be there. So let's see. I know that Lagrange error bound says that if I know a maximum value of the next derivative, and I do, I know that f triple prime of x is less than or equal to 3. So there's my cap on that. And then I have my x value, which is 5, minus 3, because the series is centered at 3. And this is my third degree term, so the next term, over 3 factorial. Right? And just in case this comes out to be negative, we are talking about the absolute value of that. And I should have put that, let me just go back here. I wrote your, back here, why don't you just go back in your notes. That also should be an absolute value, because this here, that could come out to be negative. And of course this is an absolute value, so it needs to be less than some positive number. In this case I didn't really need them, because that will come out to be positive. And let's see, what's that equal to? So 2 cubed is 8 times 3 is 24, divided by 6 is 4. So the Lagrange error bound says I'm not off by more than 4. Well, that's a pretty lousy approximation, considering that our approximation was 6. So that means that the real value of f of 5 is equal to our approximation plus or minus the error. So in other words, it's between 2 and 10. Geez, that's not very good, is it? But we, if you're wondering, like, why is it so bad? Well, we're approximating to use the second degree polynomial that we made at x equals 3, and we're trying to approximate 5. 5's kind of far away from 3. So, and this is only the second degree approximation, so I think our expectations shouldn't have been that high. But that's how you use Lagrange. And in different kinds of contexts, you just have to be aware that if somebody mentions the Lagrange error bound, there has to be some way for you knowing this, that cap on the next derivative. And I have seen, and you probably will see at some point, problems where that information was given in the form of a table of data, and you had to kind of find that in the table of data. I saw one crazy problem once where they gave a graph of the next derivative, and you just kind of had to look at the graph and figure out what that maximum would be, some kind of reasonable cap. Sometimes it's just given like this. But whichever way you can find it, that's how you use it for the Lagrange error bound for non-alternating series.